In this video, we're going to start chapter 3 of the geometry textbook. Chapter 3, you can see, is all about triangles. So we're going to learn a lot about triangles in chapter 3. But after chapter 3, we're not going to be completely done with triangles. We'll come back to different aspects of geometry related to triangles in future chapters as well. But in chapter 3, we're going to learn a lot about triangles. So in this video, we're going to go through the opening section, which is about congruent triangles. Okay, so here's the opening image for this chapter. It says majestic. In Statue Square of Hong Kong, the Bank of China, the structure shown at the left in the photograph above. So here's the Bank of China, they're saying, rises 1,209 feet above the square, above Statue Square. Designed by I.M. Pei, who studied at MIT and also graduated from Harvard Graduate School of Design, the Bank of China displays many triangles of the same shape and size. Such triangles, known as congruent triangles, are also displayed in the Ferris wheel found in one of the previous examples. While chapter 3, this chapter, is devoted to the study of triangle types and their characteristics, the properties of triangles developed herein also provide a much-needed framework for the study of quadrilaterals found in the next chapter. So a lot of the principles we're going to learn in this chapter about triangles are going to extend to quadrilaterals, and you can think even all polygons in general. A lot of the notation, the analysis techniques, etc., the framework. Okay, so, but what they're saying here, if we look at this, the Bank of China, all of these triangles they're saying are congruent. Even though they're a lot of them are oriented differently, they're still congruent. Okay, but we know what congruent means. This isn't the first time we've heard the term congruent. So if we come to the start of this section here, it says two triangles are congruent if one coincides with or fits perfectly over the other. In figure 3.1, we say that triangle ABC is congruent to triangle DEF if these congruences hold, that they're about to state here. So yeah, we've already talked about what congruence means. And the idea is that it's like congruence is a parallel to equals, but in regards to figures. So a figure could be, it's not just a polygon, it could be an angle, it could be a line segment, it could be anything. It could be 3D shapes, but it's the parallel to equals, but in relation to figures. And the idea is if two figures are congruent, what they're saying is that, so, okay, these two triangles are congruent. These two figures are congruent. The idea is that you can have separate figures that are oriented completely differently in 3D space. So all I can really illustrate to you here is within a plane, but you could really extend this to 3D space. They could be oriented completely different. Okay, but even though they're oriented completely different, they're still the same figure. They're still equal to one another, or we said they're congruent to one another. Right? So even though I rotate this, flip it vertically, flip it horizontally, right? Since all I've done is rigid body transformations, these two triangles are still the same triangle. In other words, they're congruent. That's the idea. That's the idea. That's the idea of congruence. It's saying, look, you still have the same figure, even if those two figures are oriented completely differently. It's still the same figure as long as you haven't changed the size and the shape and the scale. As long as you haven't done any stretching, shrinking, scaling, things like that, then you have the same figure as a corresponding figure, and so that they're the same figure, and meaning they're congruent. Okay, now, but the way we describe, when it comes to two numbers being equal, you just say, okay, you have the same number, right? 5 is equal to 5. But when it comes to figures, it's a little more complicated to how you describe that you have the same figure. Okay, but the idea is, as we've talked about, what it's going to come down to is that corresponding features of the figures are going to have the same measure. So features, meaning like, okay, with a triangle, what are the features of a triangle or a polygon? Well, you have sides which have lengths, and you have angles between those sides, right? So in that case, the corresponding side lengths of the two congruent triangles are going to be the same, and the corresponding angles are going to be the same. Now, if you have another kind of figure that's different from a polygon and it has other kinds of features other than just straight sides and angles, then those are all those corresponding features are going to be the same between congruent figures. Okay, but now what do we mean by corresponding? What is that about? All that's about is if you have one figure that's completely reoriented from another figure that it's congruent with, then you can, since they're the same figure, then you're able to say, okay, I could take this, since they're congruent. Another way to look at congruence is that I could take one figure, completely reorient it, and line it up and it fits perfectly on top of the other figure. That's another way to look at congruence, right? We know that I could do that here because I just reoriented this starting from this point, right? I'll flip it horizontally, flip it vertically, undo the rotation a little bit. There you go. They're congruent, right? I could line them up exactly on top of one another, right? So all corresponding means is that whenever I line them, okay, so if whenever I untransform this and I put them one on top of the other, okay, whenever they're on top of one another, if I put a marker on the A vertex and then I transformed it back to this transformed state, well, where did that A vertex go? Wherever that A vertex is, that's what corresponds to the original A vertex. Wherever the B vertex went, that's what corresponds to the original B vertex. And same idea with the sides. You have corresponding sides, corresponding angles. It's corresponding features of two congruent figures, right? And the idea is that if you have congruent figures, all the corresponding features are going to have the same measure. That should make perfect sense to you. All the corresponding features, not just of polygons, of any congruent figures, whatever has a measurable feature is measurable. Corresponding features of congruent figures or 3D shapes and whatnot are going to have the same measure. And that's why they're saying that because these two triangles are congruent, triangle ABC is congruent to triangle DEF. That's another way we indicate what features correspond to which is with how we name the figure. The naming of the figure is important. And it's important, especially with congruence, because you can see which features correspond to which. So if triangle ABC is congruent to triangle DEF, then what we're saying is that vertex A corresponds to D, vertex B corresponds to E, vertex C corresponds to F. So that means that angle A is congruent to angle D, angle B is congruent to angle E, angle C is congruent to angle F, and we can also match up the sides as well. Side length AB is going to be congruent to side length DE. Side length BC is going to be congruent to side length EF. Side length AC is going to be congruent to side length AF or DF. You see, that's the corresponding features that they're all congruent. Okay, so now I really want to stress again that how the naming of figures is really important. That should be clear to you here, not just with triangles, with any figures. The way you name the figures is very important. You want to have if you have that's why we talked about in chapter 1, if you have like a rectangle or something, you can't just arbitrarily say this is rectangle, A, D, C, B. No, you have to go in order, right? You can't just arbitrarily name figures. And this is one of the reasons why, because we use the names of figures to indicate which features correspond to which in the case of congruent figures. And just a reminder, what we learned in chapter 1 about naming figures was that, so if let's say we had the rectangle WXYZ, okay, so we could name this rectangle WXYZ, and what's really important here is that you walk consecutively around the figure. Because what's most important is that you're showing what the sides are. Like you have side WX, side XY, side YZ, side WZ. But as far as which vertex you start with or the order you walk around, it doesn't matter. So we could name this rectangle WZYX, and that would be acceptable. I mean, I guess you'd want to be nice to put it in alphabetical order if you can, but this would be acceptable. Because like side WZ is also side ZW, right? That's the same side. Or you could do rectangle YZWX, and that's acceptable. Now, if you're pairing this up with a rectangle that's supposed to be congruent to this, well, then it matters which one you put first, because you need to make sure that you make it clear what corresponds to which. But just in general, just naming in general, if you're not associating this rectangle with something else, then it doesn't matter which vertex you put first, what order you walk around the rectangle, as long as it's consecutive. Okay? All right. So we know that the symbol for congruence is, so like, okay, equals is like 5 is equal to 5. Congruence is this symbol, and you indicate a figure on one side and a figure on the other side. Where again, it's very important that you make sure that the names of the figures are it's clear on what corresponds to what. That's very important. You can't just arbitrarily state two figures and not think about how the letters of the figure names match up. Okay, because when you do that, if we've got, so triangle ABC is congruent to triangle DEF. What this is saying is that A corresponds to D. And the notation for correspondence is, if two features, or you're saying correspond to one another, you do this double arrow here. A corresponds to D. B corresponds to E. C corresponds to F. Okay, now, but what they show next, just to make this clear, is that, so yeah, we can see visually that A corresponds to D and B corresponds to E. But if you're just given this statement here, that triangle MNQ is congruent to triangle RST, we don't see the triangles. That is implying, though, that even though you don't see the triangles, that M corresponds to R, N to S, Q to T. And then since we know these are triangles, we know that we understand that, okay, that means that you have a side MN, a side NQ, a side MQ, or you could say side NM, side QN, whatever. Okay, well, since features are all equivalent in congruent figures, well, then we know that side MN is congruent to side RS, side NQ is congruent to side ST, or that they correspond. Correspondence means like equivalence, as like, well, you can't say like vertices are equivalent. There's no measure of a vertice, but if something that corresponds to something in two congruent figures has a measure, then those measures are going to be congruent. So angle A, the measure of angle, or the measure of angle M, is going to be equal to the measure of angle R. They're going to be congruent. N to S, Q to T. Right? So like with polygons, we're just talking about side lengths and angle measures, but this is going to be the case for any kind of figure. Any measure of the figure is going to if that figure is congruent to another figure, those corresponding measures are going to be equal. They're going to be congruent. Okay, so it says for two congruent triangles, the correspondence of vertices is given by A corresponds to D, B to E, C to F. So complete each statement. Triangle BCA is congruent to what triangle? If A corresponds to D, B to E, C to F. Okay, well, you would say, you just match it up. You say B corresponds to E, C corresponds to F, and A to D. Like that. Okay, what about this? What if you said triangle DEF? Because remember, you can name a figure however you want. Maybe you wanted to name it with the D first, whatever. Okay, but so what would the congruence be in this case? Well, D corresponds to A, E to B, F to C. like that. Okay, so definition. The definition of the congruence of triangles. But this definition is a simple extension to any figure. But it says two triangles are congruent if the 6 parts of the first triangle are congruent to the 6 corresponding parts of the second triangle. So yeah, when it comes to a triangle, I mean, we could do this with any figure. You could say two figures are congruent if all of their corresponding features are congruent. Well, what are the features of a triangle? There's 6 features. And when I'm saying features, I guess you could call a vertex a feature, but I'm really more talking about here measurable features. There's 3 angles, there's 3 side lengths with a triangle, right? 3 angles, 3 side lengths. So if the 6 corresponding features of a triangle are congruent to the 6 corresponding features of another triangle, then those triangles are congruent. Okay? It says, as always, any definition is reversible. Yeah, that was the characteristic of any definition. A proper definition is reversible. So what they're saying there is that if you have 2 triangles are known to be congruent, we may conclude that the corresponding parts are congruent, the corresponding features, right? Or if we look at that in reverse, if we find that the six pairs of, it'd be 6 pairs, 6 in each triangle, the 6 pairs are congruent of 2 triangles, then those triangles must be congruent. Okay? And so then it says, using the terminology from section 2.6, the previous chapter, that they take triangle QNM and reflect it about this vertical line here that they didn't show. Okay, well, we know any of those 3 basic rigid body transformation types don't change the size or shape of the figure. Translations, rotations, reflections. So if the only thing that was done here was a reflection, we're going to have 2 congruent triangles. So triangle QNM is going to be congruent to triangle, and you just match up the features. Well, we know with a reflection, it's the perpendicular bisector, so Q corresponds to T, N to S, M to R. So we can say that triangle QNM is congruent to triangle TSR. Okay, great. So that's another thing to think about, that when it comes to figures, congruent figures. So it might be hard to see if 2 figures are congruent because they're oriented differently. Well, if you have 2 congruent figures, if they're not already on top of one another, and that's like they're the same figure literally, visually as well, then they're going to have some sort of rigid body transformation applied to it. There's and no other type of transformation. They're going to have been translated, flipped, rotated, or some combination of all of those. You can't transform it another way, or it wouldn't be the same figure anymore. So it's another thing to think about. If you're looking at 2 figures and you're trying to say, okay, are these 2 figures congruent? Well, okay, if they're congruent, then how have the figures been translated, rotated, or reflected relative to one another? All right, so what they're going to talk about next are some of the properties of congruent triangles that are useful in later proofs and explanations. Okay, now it says in the figure, notice that corresponding sides lie opposite corresponding angles and conversely. So yeah, that's something that's useful. So if you know that these 2 angles are congruent, and you show that they're congruent, and then now you're kind of confused to figure out which other sides correspond to which, etc. Well, if you know these 2 angles correspond, then you know that, okay, that means the 2 sides opposite those angles are going to correspond, right? So that could be really useful. Or if you know these 2 side lengths correspond, then that means that the angle opposite those side lengths are going to correspond on the 2 triangles. Okay, so now here are those properties they talked about. So if you have triangle ABC is congruent to triangle ABC, that's the reflexive property of congruence. So this is a property of congruence, not just of congruence triangles. And that what they're talking about here, if you remember from chapter 1, was that this might seem trivial, but so like the equality has the reflexive property. 5 is equal to 5, right? The same number is equal to the same number. But like a greater than doesn't have this property. 5 is not greater than 5. right? But congruence has this reflexive property. Okay, congruence also has the symmetric property, which says that, so, okay, with an equals, you have if A is equal to B, then B is equal to A. Okay, but this isn't always the case with, like, okay, with if A is greater than B, okay, does that mean that B is greater than A? No. So, but congruence also has this symmetric property. It has the reflexive and symmetric property, and congruence also has the transitive property. So the transitive property was if A is equal to B and B is equal to C, then A is equal to C. Okay, congruence has this property as well. And that's why it was called, congruence is called an equivalence relation. We talked about all of this in chapter 1. And they're just stating these properties here because they're going to be used in later proofs and explanations. All right. So it says, it would be difficult to establish that triangles were congruent if all 6 pairs of congruent parts had to be first verified. Yeah, definitely. Hopefully it's not the case that to officially prove that 2 triangles are congruent, we don't have to match up every single corresponding feature. So there would be 6 total pairs, 3 sides and 3 angles, and verify that each one of them are congruent, or their measures are the same. Well, fortunately, we're not going to have to do that. It says, fortunately, it's possible to prove triangles congruent by establishing fewer than 6 pairs of congruences. So what they're saying is if we can just verify a portion of those 6 pairs of congruences, then that's going to be enough to verify congruence of the triangles in general. Okay, but what portion? If we can just verify that 2 corresponding sides are the same length, is that enough to say that the 2 triangles are congruent? Maybe a side length and an angle? All right, so it says to suggest a first method, let's look at this construction here in example 2. So what they do is they give us these are 3 sides of a triangle. So really they're specifying side lengths is what they're doing. They're saying construct triangle ABC with the constraints that side length AB is here, side length AC is as shown here, and side length BC is as shown here. And so they go through the whole process and construct this triangle ABC, and here it is. They started by that they first drew the length of AB horizontally, and then they incorporated the length of AC and then BC. Okay, but they talk about how this triangle could have been constructed in any order, in the sense that they could have started with side length BC horizontal here, and then from there went to AB, let's say, and maybe they could have put AB, the second side length, above or below the horizontal. There's different paths you can take to construct this triangle, and depending on the path, you're going to get some triangle that visually looks different from other triangles constructed in different orders. At least in terms of orientation, looks different. But what you would find is that so you can construct different triangles in different orders, but if you took any of those triangles and reoriented them, you could make any triangle perfectly line up on another. At least visually, from our perspective, it's a perfect match. Again, any of the triangles you construct in any order, you can reorient any of those and make them line up perfectly with any of the other ones. Okay, and so with an experiment, you could say like that, what we do is we state this postulate here, which is a postulate that we use with the side method for proving congruence of triangles. Okay, this postulate says if the 3 sides of one triangle are congruent to the 3 sides of a second triangle, then the triangles are congruent according to this side criteria or postulate. Okay, now just note that this is a postulate. This is a postulate. So what that means is that, if you remember from chapter 1, what that means is that we're never going to officially prove this postulate like we do theorems. In the sense that if we come back here, this wasn't an official proof. Like this is really the proof. If you're going to say that, how do we justify this postulate, this side postulate? Well, we do it with an experiment like this, to where our intuition shows us that there's no way we can construct a triangle in any way with these three side lengths. We could change the order we construct it. We could try any possible way to construct a triangle with these three side lengths. And no matter what, you'll always be able to take triangles constructed in different ways with these three side lengths and reorient them and lay them perfectly on top of one another. And at least when I say perfectly, I mean at least visually to our eyes, it's perfect. Okay, but that's not an official proof, but it's extremely intuitively convincing. And so with that, we state this a postulate, this side postulate. And this is really powerful, because what they're saying is that if the three sides of two separate triangles that could be oriented completely differently, but if three sides of those triangles match up in terms of length, then those triangles are congruent, which means that the corresponding angles are going to be the same. Everything's going to be the same. They're the same triangle. But they're saying from this postulate that you don't have to go verify that the angles are the same. You automatically know that the angles are the same. The corresponding angles are the same. If you can show that that three sides are congruent. Okay, so this is the first criteria that we're going to talk about as far as proving congruence of triangles, the side criteria. Okay, side, SSS. If you have two triangles that might look different in terms of their orientation in 3D space, right? We could take 3D space, and you could put a triangle over here, and then one kind of going, maybe it's out here. They're oriented completely different. But if you can show that, okay, this side length is equal to this side length, this side length is equal to this side length, and this side length is equal to this side length, then you've proved those two triangles are congruent based on the side postulate for triangle congruence. These are the same triangle, just oriented differently, which means that you automatically know that the corresponding angles are congruent. Okay, and so, yeah, this is a good time to practice. What would the corresponding angles be in this case? Well, what you do is you analyze the sides that surround the angle. So the side with one dash and three dashes are surround this angle. So it's these are the corresponding angles. Those two are congruent. 2 dashes, 3 dashes, where's that? That's here. Those two angles are congruent. And then 1 dash, 2 dashes is here. So those two angles are congruent. Okay, so they give an example here of, it says to prove that triangle ACM is congruent to triangle MBD if they're telling us that M bisects AB and CD, and they also tell us that AC is congruent to BD. Okay, well, we're not going to go through the official mathematical proof notation because we're not math majors here, but if they're telling us that M bisects AB, then these two sides are the same length. And if they're telling us that M also bisects CD, then these two sides are the same length. Well, there you go. Those triangles are congruent, which means that we know that this angle is congruent to the angle that corresponds to this in the other triangle, which we would figure that out because, okay, here's 1 dash, here's 2 dashes. So here's 1 dash, here's 2 dashes. So these two angles correspond. Okay, well, these are vertical angles, so we can just see that there. And then these two, and that we only leave at least one pair, those two are congruent. Okay, great. So now next, they give some notation that's going to help us to describe the location of different angles in sides. So like here, we were having to say that this is the angle located between this single dashed line and the double dashed line, right? So what's some official naming conventions that we can use to describe different angles and sides in this context? So it says that the two sides that form an angle of a triangle are said to include that angle of the triangle. So in triangle TUV, on the next page. Let me bring that in here. Okay, there's triangle TUV. Sides TU and TV form angle T, right? These two sides form angle T. Therefore, you can say that sides TU and TV include angle T. All right. In turn, angle T is said to be the included angle for TU and TV. So angle T is included between TU and TV, or you can say that TU and TV include T. So if we come back here, what I could have said was that, okay, the angle included between sides AC and AM is congruent to the angle included between sides MB and BD. Or if I needed to, for some different context, I could specify how angle A is the angle that's included between AC and AM. Okay, now it says, similarly, any two angles of a triangle must have a common side. And these two angles are said to include that side. So, yeah, you can look at this from the perspective of a specific side. So, angle T and angle M includes side TM. Or side TM is included between angles T and M. Okay, it says, informally, the term include names the part of a triangle that is between two other named parts. In a triangle, two sides include an angle, while two angles include a side. The two sides that include the angle actually form the angle, and the two angles that include a side share that side. So yeah, that term include, you can think about it means between. Two sides include an angle, that angle is between the sides, or two angles include a side, that side is between the angles. Or a side is included between two angles, or an angle is included between two sides. It means between. And we can think about how with a triangle that the two sides that include the angle actually form the angle, right? That's what forms an angle, two straight sides that with endpoints that meet at a common point, the vertex. So the two sides that include an angle in a triangle or even a polygon form the angle. And then in regards to a side between angles, the two angles that include a side share that side. They don't form the side, they share that side. So this is just some terminology you want to keep in mind going forward. All right, now let's look at the next congruence criteria. So the first congruence criteria was the side criteria. Next, we have side angle side. Okay, and as we look at these next criteria, what you're going to notice is that the order of these letters is important. It wasn't important with side because it's all the same letter. But if you're mixing in angles and sides into a criteria, that the order is important, because what this order shows is that we have an angle included between two sides. It's not just any angle or any two sides here. The angle needs to be included between the two sides. And so that's the criteria. If you have two separate triangles like shown here, and you don't know if they're congruent, but if you can show that two of the sides of that triangle have the same length, as well as the angle included between those two sides has the same measure, then those triangles are congruent. Then every other corresponding side length and angle is congruent. That's the side angle side congruence postulate. So, like for example, here, if we had these two triangles and we didn't know they were congruent, then just start comparing sides. We see that, okay, this side length has equal length, equal measure, equal length to this side length. Okay. Then we keep comparing sides and we find that this side length has the same length as this side length. So now we have two side lengths that match up. Okay. And then we also find that the angle included between those two sides on both triangles is the same measure. Then we know that those two triangles in general are congruent based on the side angle side criteria, congruence postulate. Okay, so now the next thing they talk about here is, this is just about some specifics on doing proofs. And what they're saying is that if you have to do if we come here, okay, for this proof here, they're saying given that PN is perpendicular to MQ and MN is congruent to NQ, then prove that the two triangles are congruent. And then, so to go through the proof, one thing you're going to state is that okay, these two triangles share a common side here, right? And so from an official mathematical standpoint, you're still going to need to make a statement that these two side lengths of the triangles are congruent. And so now if we come back here, what they're saying is that, so those two triangles share a common side in that example, and the statement that you're saying that PN, segment PN is congruent to segment PN, which is justified by the reflexive property of congruence, stating that something is equal to itself or congruent to itself, which is conventionally expressed as identity. So definition, it says in a proof, identity, also known as the reflexive property of congruence, is the reason cited when verifying that a line segment or an angle is congruent to itself. So you can think about, actually, you're going to use this with any kind of congruence. If you're stating that something is congruent to itself in a proof, then the reason you're going to cite is, you can say either the reflexive property or identity. Okay, so now if we come back here, then, I mean, we can go through an informal proof here. We don't have to do it officially mathematically. So, okay, it tells us that these are perpendicular and MN is congruent to NQ, so these two are the same length. Well, these two are obviously the same length. They're the same side, right? Okay, side, angle, side. This angle has to be 90 degrees. We see that these two triangles have, we've proven two side lengths are the same, and the angle included between them are the same. So based on the side, angle, side congruence postulate, the two triangles are congruent, which means that these lengths are the same, these angles are congruent, and these angles are congruent. Okay, but now officially, when they're going through this, you can see at this step, they need to state that for the two triangles, side PN is congruent to side PN, and they cite identity here. Okay, great. Next, we have another congruence postulate we can use, the angle side angle congruence postulate. And remember, the order of the letters absolutely matters, because it tells you what's included between in what, as far as the criteria. In this case, we know that we've proven that we've shown that two angles of a triangle, of two separate triangles, are the same measure. But then we need to show that the side included between those two angles are equal measure. Then we've proven that the two triangles are congruent. Okay, so no, it's not saying this is different. This is two different things. Angle, side angle, and side angle, angle are two different scenarios. Okay, so that's the angle, side angle congruence postulate. If we look at these two triangles, you could think about it. I like to draw this. I think 3D space is really intuitive to look at two separate triangles, or just oriented completely randomly in 3D space. So if you had, something like that, and then this was like going into the page, and who knows, something like that. If you measured this angle and got 33 degrees, okay, then you came here and measured this angle and also got 33 degrees. Then you started measuring other angles, and you got this angle was 47 degrees, and you got this angle was 47 degrees. And then you measured this side length and got 5 centimeters or whatever the units are, and then measured this side length and got the same measure. Then these two triangles are the exact same triangle. They're just oriented differently. You've proven it by angle, side, angle. Okay. Now, they note here that So they state the three congruence methods that we've talked about so far: side, 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 side angle, side angle, side angle. But they note that, something like side, side angle. If you show that two sides are of equal measure of a triangle, and an angle that's not included between the two sides are the same, that's not enough. You can't officially state that the two triangles are congruent. Now, we're going to learn in trigonometry, when we talk about the law of sines and cosines, that you have constrained the triangle a decent amount. The two triangles, they're close. They're close. They're closely related, obviously, but you can't officially state that the triangles are congruent with a side-side angle comparison. Okay, now what about angle, angle, angle? If you verify that two triangles have all their angles have the same measure, is that enough to state congruence? Well, no. Because think about it. I can take this triangle and scale it up or down. I'm not changing the angles. Right? So none of these triangles are congruent. These are all different triangles. The side lengths are different, but I'm not changing any of the angles. So no, angle, angle, angle is not enough to prove triangle congruence. Now, it does prove a relation between triangles that they're similar triangles, which we'll talk about in a later chapter, but not congruence. Okay, let's look at this example here. Given that segment AC is congruent to segment DC, AC is congruent to DC, okay, angle 1 is congruent to angle 2. Prove that triangle ACE is congruent to triangle DCB. All right. Well, they share a common angle. So based on the reflexive property or identity, angle C is congruent to angle C with respect to the two triangles. So we've got, let's see, angle, side, angle, right? So we've got two angles are congruent between the two triangles, and as well as a side length included between those two angles. So the triangles are congruent. That means this side length is congruent to this side length. And this angle is congruent to this angle. Okay, now we actually have a fourth congruence criteria, which is an offshoot of angle, side, angle. What we just learned. And the reason why I'm saying it's an offshoot is because let's say we had two angles in a side length that wasn't included between those two angles, right? So we had two angles measures, but unfortunately the side length wasn't included between the two angles. So, okay, that unfortunately we can't. There's nothing we can do with that, right? So you might be thinking, well, okay, I can't state congruence then, perhaps. Well, no, because if you have, angle, angle, side, you got two angles and a side length that's not included between the angles. Well, if you have two angles, then you automatically have the third angle because all the angles sum to 180. So you could just go find the third angle. Well, in that case, if you have all three angles and at least one side length, well, then you have the angle, side, angle criteria. You see? So with that, then angle, angle, side is another criteria, congruence criteria. And I'm saying it's an offshoot because that's why they state this as a theorem instead of a postulate, because they're going to prove this. They're going to prove the angle, angle, side. You can officially prove it based on what I just said. The fact that if you have two angles and a side that's not included between the angles, well, then you can prove that. In effect, what you have is you can turn that into having two angles and a side length that's included. Based on angle, side, angle, the triangles are congruent. So, okay, if we have these two triangles and angle T being congruent to angle K, angle S being congruent to angle J, and side SR congruent to side HJ. Can we show that these two triangles are congruent? Well, okay, because we have two angles are congruent. Yeah, I didn't state that right. It's not just that we can find the third angle. Okay, it's not just that we can find the third angle, but if two of the angles are congruent, then it's really not that we can find the angle, but we know that the third angle between the two triangles have to be congruent, right? If these two angles are the same, well, then the third angles are going to have to be the same as well. So yeah, I didn't state that right. It's not about that you're able to measure necessarily the third angle, but it's more that if you know that two angles are congruent, then that must mean that the third angle is congruent as well between the triangles. And so with that, now we've got angle, side, angle. So by angle, side, angle, these are congruent.